Firstly, the objective of this experiment is to determine the volume and density of the ball bearing. After that, to determine the volume and density of the glass block. Firstly, the vernier caliper allows you to measure external thickness, internal diameters and depths of hole to a maximum of 130 mm with a 0.05 mm approximation. The vernier calipers found in a laboratory incorporates a main scale and a sliding vernier scale which allows reading to the nearest 0.02 mm. This instrument may be used to measure outer dimensions of an object using the main jaws, meanwhile inside dimensions using the smaller jaws at the top and depths using the stem. To measure outer dimensions of an object, the object is placed between the jaws, which are then moved together until they secure the object. The screw clamp may be tightened to ensure that the reading does not change while the scale is being read. The first significant figures are read immediately to the left of the zero of the vernier scale and the remaining digits are taken at the vernier scale divisions that line up with any main scale division. Apart from that, the micrometer screw gauge is used to measure even smaller dimensions than the vernier calipers. The micrometer screw gauge also uses an auxiliary scale, which is measuring hundredths of a millimeter which is marked on a rotary thimble. The micrometer in our laboratory have a pitch of 0.50 millimeter, which is two full turns are required to close the jaws by 1.0 millimeter. The rotating thimble is subdivided into 50 equal divisions. The thimble passes through a frame that carries a millimeter scale graduated to 0.5 millimeter. The jaws can be adjusted by rotating the thimble using the small ratchet knob. This included a friction clutch, which prevents too much tension being applied. The thimble must be rotated through 2 revolutions to open the jaws, and the thimble is rotated using the ratchet until the object is secure.
The apparatus for this experiment is weighting scale, glass block, vernier caliper, ball bearing, and also micrometer screw gauge. This is the figure for vernier caliper, and this is the figure for micrometer screw gauge. This is the procedure for micrometer screw gauge. The zero error was determined. The diameter of the ball bearing was measured. Step 2 was repeated at least 3 times at different positions of the ball bearing. All of the data were recorded in a suitable table. The actual diameter reading was calculated, taking into consideration the zero error obtained earlier. The weight of the ball bearing was determined. The density of the ball bearing was calculated. This is the procedure for vernier caliper. The whole number of small divisions was counted on the fixed part of the caliper to the left of the zero mark on the vernier. The sizes of the object were given to the nearest whole number of millimeters. The first mark on the vernier was found to line up with one of the marks on the fixed part of the caliper. The value of the mark on the vernier shows how many fractions of a millimeter were needed to complete the estimate of the size of the object. The zero error of the vernier caliper was determined. The length, width, and thickness of the glass block were measured by using the vernier caliper. Step 2 was repeated at least 3 times at different positions of the glass block. All of the data were recorded in a suitable table. The actual measurements were calculated by taking into consideration the zero error obtained earlier. The weight of the glass block was determined, and the density of the glass block was calculated.
Here are the results that we obtained from the experiment.
For the analysis number 1, calculate the volume V and the uncertainty volume of the ball bearing and the glass block. To calculate the volume of ball bearing, we use the formula of V equal to 4 over 3 pi r cube. We will create 3.788 exponent negative 6 meter cube for the volume of ball bearing. Next, to find the uncertainty volume of ball bearing, we use formula uncertainty V over V equal to 3 times radius uncertainty over r. So the volume uncertainty for the ball bearing is 1.175 exponent negative 8 meter cube. Next, to find the volume of glass block, we use the formula of length times width times height. The volume of glass block is 1.57 in exponent negative 4 meter cube. Then to find the uncertainty of glass block, we use uncertainty V over V equal to uncertainty length over length plus uncertainty width over width plus uncertainty height over height. So the uncertainty for glass cube is 5.269 exponent negative 7 meter cube. For the analysis number 2, calculate the density and the uncertainty of density of the ball bearing and the glass block. Formula that we use to find the value of density for the ball bearing and the glass block is density equal to mass over volume, and the formula that we use to find uncertainty density is uncertainty density over density equal to mass uncertainty over mass plus volume uncertainty over volume. The value density for the ball bearing that we obtain is 7,338.97 kg per meter cube, and the uncertainty is 25.4047 kg per meter cube. Moreover, the value density for the glass block is 1,728.707 kg per meter cube, and the uncertainty density is 5.8356 kg per meter cube.
Every measurement has an error that depends on the situation. There are three types of error: zero error, random error, and parallax error. Firstly, the zero error has the maximum amount of error in this experiment. Zero error refers to the error that occurs when the measuring instrument registers a reading when it should read zero. For example, if a vernier caliper shows a reading when its jaws are completely closed, it has a zero error. Then there is a chance that an error will occur at random, when repeat measurements of the quantity yield different results under the same condition. This is refers to as random error. Random error may be caused by slight fluctuation in an instrument, the environment, or the way the measurement is read that do not cause the same error every time. The experiment might be performed numerous times and determine the average result to overcome this inaccuracy. Finally, the error is a parallax error. Parallax error is when the pointer of a device looks like it had a different reading when read face on. This is caused by distance between the scale and the pointer. Because they are not in the same plane, readings may be not accurate when viewed at angle. The easiest solution to avoid parallax error is to read the device directly from the front of the unit.
In summary, the volume and density of ball bearing and glass block were able to determine through the experiment. Precise measurements using vernier calipers and a micrometer screw gauge were crucial for accurately assessing the dimensions. The density of ball bearing and glass block were calculated using the formula of density P equals mass over volume. The mass of ball bearing and glass block were obtained by weighting the objects on a weighting scale. The volume for both of the objects were able to be determined by using the volume formula V equals 4 over 3 pi r cubic for ball bearing and V equals L times W times H for glass block. Our results were recorded precisely in a table provided. A detailed reading and measurements while considering the zero error were applied during the experiment. The uncertainties were also obtained by using the standard deviation formula.